Yes, we can see it.
Right? Okay, great. Okay. I think there's no way I can see both my slides and you, unfortunately. But still, let's try to make it work. So first, I would like to thank like Davide, Lorenzo, and all the organizers of the school. Thanks for the kind invitation, for the opportunity to give this lecture. And this is the first module, like the first of 2 lectures on quantum algorithms. And the second part will be given tomorrow by Sohib. And actually, in my part, and in this part of the lecture on quantum algorithms, I will give an overview of some of the main digital quantum algorithms that are first, I will present the quantum Fourier transform and quantum phase estimation, and then how they can be applied to solve linear system of equations in the HHL algorithm. And then I will give a brief introduction to some more modern techniques for linear algebra on a quantum computer. That is this technique so-called the quantum singular value transform. So this, first, please feel free to interrupt me at any time if there are questions, if you don't understand something. You have already had a wonderful introduction to quantum algorithms by Davide this morning, but still let me recap what will be relevant for my lecture. So what is a quantum algorithm? A quantum algorithm, it's a finite sequence of elementary instructions for a quantum computer. And we will consider the quantum circuit model for quantum algorithms, where these elementary instructions are initializing a qubit in the 0 state, so we can add a qubit and initialize it in 0. Or we can apply to a qubit or 2 qubits a quantum gate. And actually, there are several possible choices of the set of gates that can be applied. They also depend on the hardware that you have. But usually, if you make a reasonable choice, the number of gates that you need for a given algorithm does not depend too much on the choice that you have made. So a very common choice when you write down algorithms on papers is to assume that you can apply gates belonging to some universal set of quantum gates. And a very common set of universal gates is made by Hadamard, the C0 gate and T gate. Or another choice may be assuming that you can have a C0 gate acting on 2 qubits and generic single qubit gates. And then, of course, so you can assume an allowed operator, since in the end you need to get out a result from your quantum computation, you assume that you can measure a qubit, you can select a qubit and measure it in the computational basis that is the 0-1 basis. And then the complexity of a quantum algorithm is the number of elementary instructions that are needed when you run the algorithm. And as I told you, if you make a reasonable choice of the set of the universal gate set that you're using, this number of elementary instructions does not depend too much on the choice of this set. So we will not care too much about this detail. Okay, so here are the gates that I mentioned. Probably most of you are already familiar with them. So the Hadamard gate is the gate that sends the 0, 1 basis into the plus minus basis. So 0 is sent to 0 plus 1 over root 2. And 1 is sent to 0 minus 1 over root 2. While the T gate, it's a gate that's diagonal in the computational basis. And the 0 state is kept untouched, while the 1 state gets a phase of e to the I pi over 4. And sometimes people consider also the phase gate as an elementary gate, which is the square of the T gate. So this will be a gate that adds e to the I pi over 2, a phase of e to the I pi over 2 to the state 1. But of course, since this is the square of the T gate, you don't need to consider it as a separate elementary gate unless in your hardware you can implement it easily in an easier way than 2 copies of the T gate. And actually a fundamental property of the Hadamard and T gate is that if you combine these 2 gates enough times, you can build any single qubit unitary with any required precision. And the number of applications that you need actually scales quite well with the precision, scales as the logarithm of 1 over epsilon, where epsilon is the required precision. So if you fix it, we can fairly assume that any single qubit unitary can be applied by using order 1 elementary gates. And then we have the only 2 qubit gates that we will need, the C0 gate, that of course will, if the first qubit is in 0, leaves the second qubit untouched, while if the first qubit is in 1, it will flip the state of the second qubit, so it will apply an X gate to the second qubit. And this is the compact way of writing it, writing the action of C0. And actually, it can also be proved that having arbitrary single qubit gates and C0 gates among any couple of qubits, by composing these gates, you can get exactly any possible unitary operator acting on all the n qubits that you have. And so these are all the gates that you need for any possible unitary operations you may want to apply. Of course, we will not be interested in generic unitary operations, because these operations will require a number of elementary gates which scales exponentially with the number of qubits, and then also the runtime of the algorithm will scale exponentially with the number of qubits. But the algorithms, the interesting algorithms, are the ones which require a number of gates that is polynomial in the number of qubits that we have. And then, of course, the number of interesting unitaries, it's a tiny subset of the set of all possible unitaries. Okay, so let me give a brief overview of digital quantum algorithms. So digital quantum algorithms are all the quantum algorithms that are built up in this fashion. So are built up composing, adding new qubits, applying fixed gates, and then measuring. And then I have to say from the beginning that, for example, this framework keeps out variational algorithms, because we are not allowing so far for parametric gates. So I will not talk about variational algorithms in this lecture. And this will be covered in another lecture. So the first thing you have to learn about quantum algorithms is that actually, while there are like really a lot, like so far there are a lot of quantum algorithms that have been developed, those algorithms are mostly based on only a few basic primitive subroutines. And then if you want to study quantum algorithms, what you have to do is that you first have to study all these few basic subroutines on which the algorithms are based. And then once you know like well these subroutines, you will see that the algorithms are just mostly a combination of these subroutines with some minor variation. So what are these quantum subroutines on which the algorithms are based? The first that we will see, and probably also the main, is the quantum Fourier transform, which is a quantum counterpart of the Fourier transform for functions. And it's a subroutine that can generate algorithms that can have an exponential speed up with respect to their classical counterparts. And the main application of one of the main applications of the quantum Fourier transform is the quantum phase estimation. Which is a quantum algorithm that more or less, given a unitary that you can apply as a black box and given an eigenvector of a state, which is an eigenvector of the unitary, lets you find an estimate of the corresponding eigenvalue. And among the main application of quantum phase estimation, there is the famous Shor algorithm for factoring that can factor numbers, integer numbers in a time that is polynomial in the number of digits rather than exponential, how it's required by the best classical algorithms that are nowadays available. And the quantum algorithms for quantum linear for linear algebra, such as the HHL algorithm for matrix inversion. And also a generalization of Shor's factoring algorithm that we will not have time to cover in this lecture is the algorithm for the hidden subgroup problem, which is a quantum algorithm that more or less is like if you have a function that's defined on a group, and this function is invariant with respect to the action of some subgroup, then this algorithm lets you identify what is the subgroup with respect to which the function is invariant. And for example, like initially this may seem like a very abstract problem, but a concrete setting in which you can find this algorithm useful is the setting of finding the period of a function, where in this case, the hidden subgroup is the shift by one period, which of course leaves invariant a periodic function. Okay, leaving the quantum Fourier transform, another fundamental quantum subroutine that we will not cover in this lecture is the amplitude amplification. And more or less amplitude amplification, if you like, it's a subroutine that if you have, let's say you want to produce some target quantum state, but actually what you have an algorithm that produces a linear superposition of the target state that you want plus some garbage that's orthogonal to the state that you want. And then amplitude amplification, it's like usually the standard procedure to get your target state would be to measure in which subspace you have, assuming you can identify the bad subspace of the garbage. And then if your measurement gives you the good result, then you are guaranteed that you have produced your state. And of course, in this case, the success probability will be the square norm of the projection of the state that you produce on the good subspace. And amplitude amplification is a subroutine that gives you a quadratic improvement in this task. So amplitude amplification will not give you an exponential speed up in solving problems, but on the other way, it's much more flexible and can be applied in problems which do not have any kind of structure. And for example, the most famous application of amplitude amplification is Grover's quantum search algorithm, which allows you to find a marked item in an unstructured database in a time which is proportional to the square root of the number of entries of the database. And a variant of Grover's search algorithm is the algorithm for quantum counting, which instead of allowing you just to find a marked item, like in this case, we assume that there is more than a single marked item. And this algorithm will allow you to find out how many marked items are there, so to count the marked items, and also to be able to sample one of the marked items. Finally, the last fundamental subroutine that I will talk you about is what is called the quantum singular value transform. And this is a very recent result of the past, the initial paper is from Fourier only 4 years ago, while on the other side, the Fourier transform and amplitude amplification are results from the 90s. And it provides a very flexible framework that has allowed to unify several quantum algorithms. And you will see more about this in the last part of this lecture. Okay, so let's start from the first subroutine, which is the quantum Fourier transform. So if we have, like we said, we have the computational basis for a single qubit, which is the Z1 basis. And if instead we have n qubits, the basis for the computational basis for n qubits, like the basis elements are labeled by strings of n bits. So you can see here an example string of n bits where each bit corresponds to a single qubit. But the fundamental thing that will be like a key point for this algorithm is that a string of n bits can also be thought as the binary representation of some natural numbers that goes from, of course, in this way, we can get all the numbers that go from 0 to 2 to the n minus 1. And actually, in all this lecture, we will consider bit string x at the same time as bit string and as a natural number in binary representation. And you will understand from the context every time what is the interpretation that's used at the moment. So let's start from the classical Fourier transform for functions. You will all be familiar with this, I assume. If you have a real valued function on the real line f, you can define its Fourier transform. and its Fourier transform computed on in the point k, it's equal to the integral of f of x e to the I kx dx. Now, instead of having a function defined on the real line, we have a wave function for n qubits. And as I told you, a wave function for n qubits has as a domain a string of n bits that can be considered as a natural number from 0 to 2 to the n minus 1. So we have a wave function defined on natural numbers, and we can define a Fourier transform of this wave function more or less in the same way. So we replace the integral by a sum, and then everything stays the same. We add this normalization factor 1 over 2 to the n over 2 in front, because in this way, the Fourier transform operation, it's exactly unitary. And then we sum over all values of x, psi of x, times e to the 2 pi I x y over 2 to the n. And of course, we have to divide by 2 to the n here in the exponent. Otherwise, since x and y are both integers, this exponential will trivially be 1. And here, of course, this Fourier transform of this wave function will be another wave function which is still defined on bit strings or on integers in binary representation. Okay, then let's go to the next line. Of course, if we know the action of, like, first you can check by hand that this operator that I called QFT, it's linear and unitary. And then, since we have the action on a generic wave function, we can easily find out what its action on a Dirac delta wave function is. And this is the action of the quantum Fourier transform on a basis vector, which can be expressed in this way. And it's easy to check that these two expressions actually agree. Now, if we want to build a circuit for the quantum Fourier transform, which we will do in the next slide, it will be fundamental to recognize that this state that we obtain applying the quantum Fourier transform to a vector of the computational basis is actually a tensor product. And it's a tensor product of this form that you see here on the right. Now, a fast way of convincing you of the validity of this equation is that, so each factor here is associated to a digit of y in the left. And of course, here you see that if the kth digit of y is 1, here this will bring you a phase of e to the 2 pi I x over 2 to the k, which agrees with what you have on the left-hand side, because the kth digit, like switching the kth digit of y, since we are counting digits from the left, this digit will have a value of, like, we change the number by 2 to the k. And then if you change such digit of y here, you can check that this is the shift in the phase that you get. Okay, now let's see what the circuit for the quantum Fourier transform is. So first, a nice thing about unitary operators is that they are linear, and then once you have defined them on a basis, you have defined them everywhere. And then, of course, so when we are building a circuit for a given quantum operation, we only have to check that the circuits behave as expected on the vectors of the computational basis. And if they behave as expected on those vectors, then they will behave as expected in general on a generic linear superposition of the basis vector. So let's consider an input which is a vector of the computational basis. Here you see it. And you may be already familiar with these circuit diagrams. Here, horizontal lines represent qubits. Time usually goes from left to right. And then here you see that we have like these H are Hadamard gates. And then we have these gates here, which are like the black dots represent controlled gates. So the black dot is placed on the qubit, which controls the application of the gate. And then these gates in the circle are the gates that are applied when the control is active. And like we label them, they are labeled here as RK. And these RK gates are single qubit gates that are diagonal in the computational basis. So they leave the zero state untouched, and they add a phase of e to the 2 pi I over 2 to the k to the 1 state. So why does this circuit do its job? Let's check it. Let's go back to see what was the state that we have to build. We have to build this tensor product here. So what happens? Let's see what we are doing with this circuit. First, let's consider the first qubit. What happens to the first qubit? It first undergoes a Hadamard gate, which is the same, which adds to it a phase, like a Hadamard gate applying to a qubit in the computational basis state X is the same as applying a phase of e to the 2 pi x over 2, because it does nothing if the, sorry for this, no. This Hadamard gate puts these qubits in a superposition of 0 and e to the 2 pi I 0.x1 over root 2, and that's what we can see here, where the Hadamard gate is applied to the last qubit. I'm sorry for, because when I prepared this lecture, I was supposing to be coming there, and I suppose, like, I thought of using the Blackboard to help me present this this circuit diagram, but now I will try to do it without backboard since I don't have other choice now. Okay, so this Hadamard gate, like this expression that you see here is in the exponent is a decimal number expressed in binary form. So it's 0.x1 up to xn. And of course, this is exactly the same as the binary number x divided by 2 to the n. So you will recognize that this Hadamard will create here a superposition of 0 with e to the 2 pi I 0.x1. So this is the first term that you see here. And then you see that on this gate, on this qubit, we will act with all the controlled operations R2, R3 up to Rn. So this controlled operation, they depend on the state of the other qubits, and they will all add all these phases that appear here in this decimal expansion. So R2 will add the 0.0x2 that you see here, and then R3 will do the same with x3 up to Rn that will add up this phase 0.0000 with xn in the end. And you can check here that, like, if you compare these powers of 2 to the k, which are in the definitions of these RK gates, with the position of the digit that you see here, you can check that they all match. So after applying all these gates, the state of x1, it's what it should be. It's this one. And then we can continue. And the next part of the circuit will build the right state for the second qubit. So we first apply the Hadamard gate to obtain this 0 plus e to the 2 pi I 0.x2 state 1. And then we apply all the rotations which are controlled by the following qubits, which build up the rest of this of the decimal expansion of this number. And then this goes up to the last qubit n. And of course, in this last qubit, we apply only the Hadamard gate that puts it in this superposition of states 0 plus e to the 2 pi I 0.xn 1. Then if you compare the state that we got with what we had here in the previous slide, here we can see that the term with that should be there in the first qubit is what here appears in the last qubit. And then you realize that this is the correct outcome of the quantum Fourier transform on this basis state, but the output qubits are in the reversed order. And then what you need to put them in the correct order is to apply a sequence of swap gates that can be obtained from combining 3 CNOT gates that reverse the order of these qubits and finally gives us the quantum Fourier transform in the right order. Okay, and actually, if you count how many gates we needed to implement this circuit, so you will find that the order, like the number of gates that we need scales as the n square, where n is the number of qubits, because to the first qubit, we applied, like we have n gates applied to the first qubit, n-1 applied to the second, n-3 applied to the third, and so on. So this already gives us order n square gates. And then the swap gates, like since reversing the order of this can be realized with order n swap gates, and then we require order n square gates to implement this quantum Fourier transform. Okay, now, in principle, you may think that the quantum Fourier transform can be applied to speed up the application of a Fourier transform to a function defined on a discrete set. But actually, this is not so, like this application is a bit tricky because, like, first you would have to encode your function in a quantum state, and then you need to, like, read out the result, because you will have a Fourier transform that's encoded in the amplitude of a quantum state that you know you're not allowed to read directly, but you have to perform measurements to read this amplitude. And then since there are, like, these amplitudes are exponentially many, of course, if you want to find, like, a single amplitude can be exponentially small, and you may need an exponential number of measurements to find an estimate of that amplitude. So this application of the quantum Fourier transform that will seem to be trivial, it's actually less trivial. And so, but there exist different applications of the quantum Fourier transform where you can show on more rigorous basis that you have a speed up with respect to the classic, what you can do classically. So one of the main applications of the quantum Fourier transform is the quantum phase estimation algorithm, which was I anticipated a few minutes ago. And the setup is the following. So let's say we have unknown unitary operator U that we can apply as a black box. And U acts on m qubits. And let's say that we have a quantum, like a set of qubits that are in an eigenstate of U, and we will call little u this eigenstate. And this eigenstate will have an unknown eigenvalue that we parameterize as e to the 2 pi I phi, where phi runs from 0 to 1. And our goal is to find phi. So how does the algorithm work? Let's define this unitary operator V that acts on our m qubits plus n ancillary qubits. And what V does is the following. So let's say that we apply V to a product state that is made by a basis state for the auxiliary qubit tensored with a generic state for the m qubits. And of course, since these states span the whole joint Hilbert space, this completely defines our unitary operator V. So what V does is that it reads the value of the state. It considers this label of the basis vector of the auxiliary qubits as a number in binary form, as we have done before. And then it applies the unitary U to the second subsystem a number of times that's equal to the, like, that's given exactly by the number X that labels the basis state of the auxiliary qubits. So V acting on X tensor psi will be equal to X tensored with U to the X psi. Now, the idea is to use V to find the eigenvalue of U. And how do we do this? Like first, we produce a state which is a uniform superposition of all the possible basis states, which is the state here. Then we append our eigenvector U to the state that you see here. And we apply V to this object that you see here. What does it happen? Of course, V will read this value of X and will apply the unitary X times. And then we know that U is an eigenvector of the unitary. Then what you will get here is the eigenvalue to the X power, which is what you see. Now, this expression should remind you of something. Because if we go back a couple of slides and you see this expression here, you will see that like these two expressions are very similar. And actually, if phi is an integer multiple of 1 over 2 to the n, this state that you see here is exactly the quantum Fourier transform applied to the state 2 to the n phi, which in this case becomes an integer, and then this can be taught as a basis state of the n auxiliary qubits when the integer is expressed in binary form. So of course, if we know that this state is approximately this, we can apply, like it's spontaneous to apply to this state the inverse Fourier transform on the first register, and then measure our n auxiliary qubits. And then in this way, we will get the value of phi. And then you can ask, okay, but what happens if phi is not an integer multiple of 1 over 2 to the n? For example, phi may be not a rational number. Then in this case, it becomes a bit more tricky. You have to go through a bit of calculations, but what you find is that you can apply the same procedure. And with high probability, what you get is an estimate of phi, which is accurate to roughly n bits. Actually, you get a bit less of that, like there is some price you have to pay. So you have n minus some bits of accuracy of this estimate, but still the same procedure keeps working. So, recap, you create this uniform superposition, you apply this V, then you apply the quantum Fourier transform, you measure the first register, and then you directly get an n-bit estimate of phi, and then an n-bit estimate of the eigenvalue of the unitary operator that we wanted. Okay. Then, as for the quantum Fourier transform, we can, let's see, an explicit circuit that does this. So this is a bit simpler than the circuit for the quantum Fourier transform. So first we have to create the uniform superposition of all states, and we do this by applying a Hadamard gate to each qubit. And then we have to apply the unitary operator U a number of times that depends on the number which is encoded in the vector of the canonical basis associated to the first n qubits of the auxiliary n qubits. So what does it mean? It means that, for example, this is the last qubit will be the least significant digit. So if we change this digit, the number will change by 1. And actually here you see a control U gate, which applies U a single time. If we go into the second qubit instead, if we change that digit, the number will change by, of course, by 2. And actually here we see a control U gate, which applies U square. So if this digit which changes, this control applies again the operator U square to the target qubits. Okay, and this continue, you can continue this up to what qubits, up to the most significant digit. And of course, if you change the most significant digit, you will change the number by 2 to the n minus 1. And then for this reason here, you have a control U gate where you apply U 2 to the n minus 1 times. And all this part of the circuit applies U to the x, where x is the number encoded in the label of the computational basis of the first n qubits. And then, of course, you plug in the inverse quantum Fourier transform on the first n qubits. This is the inverse of the circuit that we have seen before. And of course, you can easily find the inverse circuit because you can invert the circuit that we have seen gate by gate. And then we measure the first n qubit and we get the answer. So how many gates do we need for this? We know that like we have n gates, n Hadamard here. Then we have order n square gates in the quantum Fourier transform. And then we have this calls to the control U. And actually, these calls to the control U, they call a U that can be applied up to the n minus 1 times. So the number of gates that we need to build for this circuit depends a lot on how many gates we need to apply U. In particular, if to apply U several times, like if applying U several times has to be done sequentially and there is no shortcut, then this will be the bottleneck of this algorithm because we will need to pay, we will need a lot of gates to apply U 2 to the n minus 1 times. We will need exponentially many gates. While this algorithm will be quite fast if we have some shortcuts that allows us to avoid applying U sequentially to get it, to apply it a large number of times, but we can do it in some way altogether. Okay. Now we've seen this algorithm for quantum phase estimation. This is still a subroutine. Let's see how we can apply this subroutine to speed up linear operations in linear algebra. So we will see, like I will present the so-called HHL algorithm, which like HHL stands for the initials of Harrow, Hasidim, and Lloyd, who invented this algorithm in 2009. So what is the problem that we are going to solve? Let's say we have a sparse Hamiltonian H that acts on m qubits, where sparse means that each row of the Hamiltonian has only, like the number of non-zero elements of each row is order 1. So a very simple example of sparse Hamiltonian is the Hamiltonian proportional to the identity, where each row has only a single element, which is non-zero. But then there are still like probably most of the Hamiltonians which are like relevant, represent actual physical models, are sparse. And then also given a quantum state psi, which we have in a physical form, our goal is to build a quantum state which is proportional to h-1 psi. And of course, I have to say proportional to, because h-1 is not a unitary operator. And then in general, h-1 psi will not be normalized. Actually, this algorithm was proposed in, let's say, two versions, one for sparse Hamiltonians and one for Hamiltonians which have low rank. But then what happened is that there was a discovery a few years ago by Ewing Tang mainly, which more or less she proposed a completely classical algorithm that is it's inspired by this quantum HHL algorithm that allows us to like solve the same problem completely classical with only a polynomial overhead with respect to the complexity of HHL. So the corresponding classical problem is, let's say that like instead of having the quantum state psi, we can access the single entries of psi, and then we have access to the probability distribution that we get if we measure psi in the computational basis. Then if we have this dequantized algorithm proposed by Ewing Tang, what it gives you is that it gives you access to the probability distribution that you get by measuring h-1 psi in the computational basis. And then more or less this classical algorithm, like if the problem that you have to solve it's entirely classical, this classical algorithm has only a polynomial overhead with respect to HHL. And then most people consider that this kind of quantum algorithms for linear algebra do not really have an advantage when the involved matrices are low rank, because then we can employ this quantum-inspired classical algorithms. And that's why in this lecture, I will focus on the sparse case. That's the relevant case where people are still convinced that no classical version of this algorithm with only a polynomial overhead in the runtime can exist. So let me now present the algorithm. So in principle, we can, like, at least formally, we can diagonalize our Hamiltonian. So this lambda k will be the eigenvalues, and this uk will be the eigenvectors. And then, of course, at least formally, even if we don't know what are the eigenvalues and the eigenvectors, our state psi can be expanded in the eigenbasis of H. So this psi k will be coefficients, and uk are still the eigenvectors of H. Then the idea is that we can apply quantum phase estimation, so the unitary that's obtained applying time evolution with this Hamiltonian for a unit time. And we can apply this quantum phase estimation to the state psi that we have. And I have to stress that like this part of the algorithm actually requires Hamiltonian simulation to be able to apply this unitary that's given by the time evolution induced by H. And you will see, I will not present in this lecture how Hamiltonian simulation works. You will see it probably tomorrow, I think. how this works. So the Hamiltonian is sparse, and that's what this is the condition that allows for an efficient simulation of the Hamiltonian and an efficient implementation of this unitary. So what does it happen? Like, in principle, I described you quantum phase estimation in case where the vector is already an eigenvector of the unitary, but if we have a linear superposition of eigenvectors, since the quantum phase estimation is a unitary operation, what we will get, it's a linear superposition of what we get with a single eigenvector. And then this is what we will get. We will get a superposition over K of psi K. We will have the eigenvector UK. And then the quantum phase estimation algorithm will give us an estimate lambda K of the eigenvalue of lambda K. Okay. So probably I should have put a tilde here, because this lambda K that you see here, of course, it's an estimate of the true eigenvalue. And in general, it will not be exactly the same as the true eigenvalue. And of course, the precision of the estimate will depend on the number of auxiliary qubits that we have. Okay. Then what's the idea? Now we have we have the value of this eigenvalue that's written in a register. And the idea is that we add an auxiliary qubit in the state 0 in this fashion. So here is the register with the estimate of the eigenvalue. We add this auxiliary qubit. And then what we do is that we apply a rotation sorry. We apply a rotation on the auxiliary qubit, and the rotation angle depends on the estimate of the eigenvalue. So the rotation will be the following one. You can check that this vector here is it's normalized, like the sum of the square of the coefficients is 1. And the idea is that we want the amplitude of the state 1 to be proportional to 1 over lambda. And then the amplitude of the state 0 is whatever we need to keep the normalization of the state. Now here you will see that we need to insert this normalization factor. And this, of course, it's because this lambda k can be smaller than 1. And if this lambda k is smaller than 1, then what will happen is that already the norm of this term will be larger than 1, which will not allow which will not allow this vector to have a global norm equal to 1. And then we have to divide here by the operator norm of H inverse, which is the largest in absolute value, the largest eigenvalue of H inverse, which means here multiplying this by the magnitude of the smallest eigenvalue of H. Okay, then let's put together what's the whole state that we have after this step. So let's remind that we started from here, from this state. So we will still have sum over k, psi k, uk, lambda k. And then instead of 0, we have this rotated vector. Then the idea is the following, that we can measure this auxiliary qubit. and we can post-select on getting the outcome 1. So what does it happen? If we do this operation, this will kill this component with the 0. That's what we do not want. And we are left with the component with the 1, which is this object here that you still see. And of course, since we are post-selecting, the square norm of this vector now is strictly smaller than 1. So what we have still sum over k, psi k. This is the estimate of the eigenvalue. This is uk. This is 1 because we are post-selected. And then we have this normalization factor that we have introduced before. And then we have the inverse of the eigenvalue. And this is starting to look like what we want because the inverse of the eigenvalue has appeared.
Sorry, Giacomo.
Yes.
Maybe you can say what you mean by post-select. Maybe not everybody is familiar with that.
Okay, sure. So post-selecting means that we discard all the runs where we get outcome 0, and we continue only if the outcome is 1. Okay. Now, this lambda, it's here, but we would not like it to be here because it should not be in the final state. And the way to get rid of this lambda is a technique that's called uncomputing, which consists simply in applying the inverse of the unitary of quantum phase estimation. And if everything works in the right way, applying the inverse of quantum phase estimation has exactly this result in like removing this ket corresponding to the estimate of the eigenvalue. And then we can also discard the ancillary state in 1, and we are left with this state here. Now, since we can remember that this lambda is the eigenvalue of h, and then this 1 over lambda k can be seen as applying h inverse to this eigenvector uk. And then we have this equality here when we replace the 1 over lambda k uk with h inverse uk. And then we remind that like we can see here that we can build again the linear combination that builds the state psi that we had in the beginning. So sum over k psi k uk is equal to psi. And then we finally see here in the end that we got the actual state that we wanted. So what's the success probability of this? The success probability will be the square norm of this state. And of course, the fact that the success probability is not 1 depends entirely on the post-selection that we have made. So this is the square norm of this state, and actually you can easily check that this quantity, like since this h minus 1, sorry, all the eigenvalues of h minus 1 are always larger or equal than the inverse of the largest eigenvalue of h. This success probability is always upper bounded by 1 over maximum eigenvalue of h square, maximum eigenvalue of h minus 1 square. And this number that you see here in the denominator is the square of the so-called condition number of h. And the condition number of h is exactly the ratio between the magnitude of the maximum and minimum eigenvalue. Okay, so this means that this the success probability will be high if the, let's say, maximum eigenvalue of h divided by minimum eigenvalue of h is still a quantity which is order 1. While this success probability can be exponentially small if this condition number is exponentially large in the number of qubits. Now, we can actually apply here this technique that I mentioned earlier in the talk, which is called amplitude amplification, because here we are exactly in the situation that I talked about. Like, we have a good state which is in some subspace, and we have a bad state which is in the orthogonal subspace. And we actually produce a linear combination of the two, but we wanted only the good part of the state. And amplitude amplification allows us to raise the success probability quadratically. So this 1 over k squared, thanks to amplitude amplification, can become 1 over k. And then, of course, we need to repeat until success this protocol. So we need to repeat the protocol k times. Now, the runtime of this algorithm mainly depends on the phase estimation part. And actually can be shown to be k squared n over epsilon, where epsilon is the precision that we require in the approximation of the state h-1 psi. And actually, let's say the bottleneck of this version of the HHL algorithm is exactly this bad scaling with the precision, this 1 over epsilon scaling. And this can be traced back to quantum phase estimation. And in particular, it can be traced back, you remember that I told you before that the complexity of quantum phase estimation depends a lot on whether you have shortcuts to implement this U elevated to a high power or not. Now, in this case, the U that we have comes from Hamiltonian simulation. So the question becomes whether we have shortcuts to simulate our Hamiltonian for an exponentially long time. And actually, the answer is no. We usually, unless the Hamiltonian is some special structure, if our Hamiltonian is a generic sparse matrix, then no, we can't. We can't simulate it with shortcuts. And then we will, if we want a high precision in preparing our final state, we will need to estimate our eigenvalues of H with high precision, because here in particular, small eigenvalues will be important. Estimating eigenvalues with high precision means that we need to apply our unitary for many times. And this means applying Hamiltonian simulation for a long time, which requires a high complexity. And that's why the scaling with 1 over epsilon. Okay. So what do we get? The main goal achieved by the HHI algorithm is an exponential speedup to solve to apply the inverse of a matrix to a vector, which can be seen as a way to solve a linear system of equations, because actually the state h-1 psi is the state, the unknown state, such that that solves h applied to the state is equal to psi. And this is a linear system of equations. And we have an exponential speedup because the runtimes is linear in the number of qubits, and linear in the number of qubits means logarithmic in the dimension of the Hilbert space, while of course any classical method to solve a linear system of equation scales, usually it scales with the cube of the dimension of the Hilbert space, but still usually at least to write, you need at least the dimension of, if you want to write down the solution in a classical form, in a complete form, you need a complexity that's linear in the dimension of the Hilbert space. However, this exponential speedup comes with some caveats. So the first caveat is the that we need to prepare this initial state psi. And of course, psi contains exponentially many amplitudes. So if we need, like if there are no shortcuts to the preparation of psi, the speed up may be destroyed by this, because we may need exponential time to prepare the initial state. But there can be some special cases where the preparation of the initial state has some shortcuts and can be done in a short time. And then, on the other hand, the second caveat is the fact that then we have the solution encoded in the amplitudes of a quantum state. So we have a quantum state proportional to h-1 psi, which is the solution of our linear system of equations. And of course, if we want to measure all the amplitudes of this quantum state, we will need an exponential number of copies, and this will destroy the speed up. But there can be some information that we can still extract by only with a small number of copies of the state. For example, if we just want to sample from the measurement in the computational basis of the state, few copies are enough for this. Then in the whole, I presented just the easier version with where the matrix to be inverted is Hermitian, but I have to say that there is a trick that adds a single auxiliary qubit, and this trick allows to handle matrices that are non-Hermitian, so this is not really a constraint. And another fundamental thing that I have to say is that if you look back on how we built the algorithm, like the inverse function appears here when we apply this conditional rotation to the qubit. And you can very easily see that it doesn't really matter whether this function is the inverse, it would have been any other function. And actually this algorithm allows us to produce any state of the form f of h psi, where f is some generic function. And of course, the runtime may depend on what f is, and in particular, it depends, like, if f has some singular points, the singular points will be crucial in determining the precision with which we can produce this state. And you can find, like this is the original reference for this HHL algorithm for linear system of equations. Lorenzo, how much time do I have?
About 10 minutes, but we are in no rush, so take your time.
Okay, we started a bit later, if I remember. Okay, so let's see first an application of HHL. So we are in a conference, like this is a school that's meant to be on quantum simulation. So the closest application of HHL to quantum simulation is applying it to solve linear differential equations. So this is the setup that we consider. We have a linear differential equation of this form. So the x of x is a vector that lives in Rn, where n is much larger than 1. And then we have the equation is x dot equals to ax plus b, where A is a sparse matrix and B is a constant vector. And actually here we have been more precise. So we say that A is S sparse if each row and each column of A have at most S non-zero elements. So here you can easily see that if B is 0 and A is anti-Hermitian, we recover the unitary evolution. And then if X is encoded in the amplitudes of a quantum state, it's quite easy to implement on a quantum computer, because this is, again, Hamiltonian simulation with a sparse Hamiltonian. So, of course, the interesting case of this algorithm is when A is not anti-Hermitian, and then this does not trivially reduce to Hamiltonian simulation. In this case, we will need some hypothesis, because this equation can have the vector x blow up exponentially with time. And if this is the case, then we will need, if we want a given precision, the solution with a given precision, we will need an exponentially high precision for the initial data. So we assume that the eigenvalues of A have negative real parts, such that there is no exponential blow up of the solution. And then what the algorithm does is that it discretizes this time evolution with time steps that are of the order of 1 over the operator norm of A. And then we will call capital K the total number of time steps that we will need. Actually, I will present, let's say, the simplest version of this algorithm, which is the first which has been developed. But then there have been, building on this simple version, there have been several improvements which have led to significant improvements in the runtime. But still, if you want to get the idea on how the algorithm works, probably the first version is the easiest to understand. So the idea is to consider what is called the quantum history state of the evolution. And what is the history state? So this history state is a quantum state of 2 registers. The first register encodes the solution of the equation at time t. And the second register, encodes the time. So the time, so the number of the step. And this quantum history state, I write here, in this way, the state is not necessarily normalized. It's a sum from 0 to k of the solution at the ith time step, tensored with register in I. Okay, so we apply the Euler forward method to solve the ordinary differential equation. And Euler forward method means that we discretize the equation. So, okay, here on the left, we have the initial condition, x0 is equal to some x bar. And then here we have a discretized version of the derivative, of the time derivative of x. So x at time at step I minus x at step I minus 1 divided by time interval. And this is put equal to matrix A applied to x at step I minus 1 plus b. Now, the fundamental the fundamental observation to be made is that this discretized version of the linear differential equation is equivalent to a linear constraint on the quantum history state. Let's see a bit better how it works. So we define this matrix M here, that you see. And then if we apply this matrix M to the quantum history state, that's what we get. And here, that's what we should have, because x0 should be the initial condition x bar. And then here you see directly appearing this quantity, like here we see the difference between x at step I minus x at step I minus 1 minus delta t times matrix A times x at step I minus 1. So if we employ this discretized version of the equation, this is exactly equal to delta t times the vector b. So imposing the like this discretized version of the linear differential equation, it's equal to this linear constraint on the quantum history state. And actually, then we have an easy way to find the quantum history state from the linear constraint, because if we know that M applied to psi is equal to this state, then we can also get psi applying M inverse to this state here. And of course, the idea is to apply the HHL algorithm to generate the quantum history state in this fashion. And now, of course, we have the solution of the differential equation encoded in this quantum history state. So the solution is still encoded in the amplitude of a quantum state. And what we can do is that we can measure it to extract the information that we need on the solution. Because as usual, if we want the whole solution, this has a complexity that scales at least linearly with the dimension of the vector space where the equation is defined. But there is still the hope that some partial information can be got with some measurements with a complexity that's still logarithmic in the dimension of the vector space and linear in the number of qubits of the register. Now, what's the runtime of this algorithm? For the runtime, I will give you the runtime of the improved version. And actually, this is the reference where you can find the improved version of this algorithm. So the runtime is proportional to the condition number, oh, sorry, this is not a condition number. This is defined, this kappa is defined in this way. So let's say that we can diagonalize A with this invertible matrix V, and kappa is the condition number of V, of this V that's needed to diagonalize A. So kappa is not the condition number of A. Then it's proportional to the runtime is proportional to this condition number of V. It's proportional to the time for which we want to simulate the differential equation. It's proportional to the operator norm of A and to the sparsity of A. And you can find all the details of this refined version of the algorithm in this paper. Okay, now if Lorenzo gives me a few extra time, I can present the quantum singular value transform. Like how much time do I have now?
In principle, you have a few minutes, but go ahead, I think.
Okay. So what's the... Actually, I will present the quantum eigenvalue transform, which is a simplified version of the quantum singular value transform, but it will still keep all the basic, all the key ideas are there, and also several of the applications of the quantum singular value transform can be made with the quantum eigenvalue transform. So what is the goal of the quantum eigenvalue transform? Like, given a state psi, we want to produce a state proportional to f of h psi, where f is an even or odd function and h is some Hamiltonian. And this should look quite familiar to you because we have seen this before for HHL, for example. And for HHL, f was the inverse function, which is actually odd. But then I told you that the same techniques can be employed to apply a generic function. Now, what is the advantage of this technique with respect to HHL? The main advantage is that we get rid of that bad scaling with the precision 1 over epsilon. And the scaling 1 over epsilon will be replaced by an exponential improved logarithm of 1 over epsilon. And this will be because this procedure completely avoids using the Hamiltonian simulation subroutine and proceeds in a completely different way. So to see how this works, all this quantum eigenvalue transform is based on a technique that's called block encoding. So what is a block encoding? We say that a unitary operator U is a block encoding of a Hamiltonian H if more or less H is a block of U. So U in some bases has this form where we have H in the top left block and we have something else in the other blocks. Now, it's often useful to consider block decompositions that correspond to a tensor product. So if Cn is the Hilbert space where H acts, we add an auxiliary qubit and then we tensor with C2. And then if this block decomposition is the block decomposition corresponding to this tensor product, we can also say that H is given by this, let's say, partial matrix element of U, because actually considering this matrix element with 0 has exactly the effect of selecting this upper left block of U. Now, of course, since the operator U is unitary, what is in this upper left block needs to have operator norm at most 1. This may, in general, not be true for the Hamiltonian that we want, but of course, we can always rescale the Hamiltonian such that the operator norm becomes smaller than 1. And from now, we will consider this rescaling to be implicit and always there. So H will be rescaled such that this requirement is satisfied. And what this quantum eigenvalue transform will produce is the possibility to apply a unitary operator that is a block encoding of f of H. So this means that applying U a given number of times, we will be able to effectively apply this effective unitary operator U tilde that has f of H in the upper left block, or f of H is obtained as this partial matrix element of U tilde. Okay, so how does this work? So let's formally diagonalize H. So lambda are the eigenvalues. So we will denote with lambda also we will label with lambda also the eigenvectors of H. And since the operator norm of H by assumption is at most 1, all these eigenvectors lie between -1 and 1. Now, actually, it will be easier if rather than dealing with a generic block encoding, we consider a specific one, but all that I will say will still hold when considering generic block encodings. So we can write down an explicit block encoding of H in this way. So you can check by hand that this matrix is unitary for any H. And actually, we can, if we consider this diagonalization of H, we can write this matrix as a sum over lambda of the projector on the eigenvector lambda of H, tensored with a unitary matrix U lambda, where this unitary matrix U lambda is the unitary matrix, the 2x2 unitary acting on the auxiliary qubit that we added for the block encoding. And this U lambda has exactly this form, and it's very easy to check this equation. Okay. Then, how does the quantum eigenvalue transform work? So the idea is that we want to build up a block encoding for f of H by applying several times U dagger and some operations on the auxiliary qubit. So this is what we will have. Here we apply a string of operators that are like here, as you can see, we are alternating application of U, a rotation in the Z direction, in the Z axis on the auxiliary qubit, application of U dagger, another rotation along the Z axis on the auxiliary qubit. And we combine this operation several times. Now, if we consider the expression for u that we had before when we, let's say, make explicit the separation of the two tensor, like the auxiliary qubit from the target system. What happens is that here, this we can see that what happens is independent for each lambda. So we can write this u tilde as a sum over lambda of the projector on the eigenvector lambda tensored with this object here that you see on the left. Now, how does this object on the left look like? You can, by hand, check that this object on the left is always a unitary matrix that has this form. So here in the top left corner, we have a polynomial p of lambda. In the bottom right corner, we have the complex conjugate of p. And then we have in the top right, I polynomial q of lambda square root 1 minus lambda square, while in the bottom left, I complex conjugate of q square root of 1 minus lambda square. And then, okay, here we applied d times u and d times u dagger for a total of 2D applications of u. Sorry, 2D applications of u or u dagger and 2D rotations in the z direction. And we can check that the degree of p is always at most 2D, and the degree of q is always at most 2D minus 1, and that p is always an even polynomial, and q is always an odd polynomial. And also this matrix has to be unitary, and this is equivalent to P and Q satisfying this condition. Now, this will seem quite involved and not so much useful, but then there comes the fundamental property. And the fundamental property is that if you take any two polynomials P and Q satisfying these three properties, so the degree of P is at most 2D, the degree of Q is at most 2D minus 1, P is even, Q is odd, and P and Q satisfy this equation, then there will exist some phases to be put in here, such that U tilde has, U tilde has exactly this form here with P and Q. So the polynomials with these properties are exactly, like these properties exactly identify the set of polynomials that you can get. And in particular, this U tilde will be a block encoding of P of H, where P is the even polynomial. Then, if we want P to be a generic even polynomial, we still have to get, because if you remember, the condition also requires the existence of an odd polynomial Q that satisfies the equation. And that condition, in principle, it's non-trivial. But still, we can play a further trick, and we can add a further auxiliary qubit. And with this further auxiliary qubit, we can get rid on the constraint on the existence of the polynomial Q. And then we get, and also, it's not necessary that P is, I've shown you the case where P has even degree. But if we stop here after an odd number of iterations, you can check that in this way we can get P with odd degree. So also odd polynomials can be obtained. Then summarizing, that's what we can have. Let's say that we start from a block encoding U of some Hamiltonian H. And let P be a generic polynomial that has degree D and it's even if D is even, and odd if D is odd. And let us assume that when the argument is between -1 and 1, the absolute value of P is less or equal than 1. Then it can be proved that we can always realize a block encoding of P of H with the applications of U or U dagger and the phase shifts or rotations in the Z direction on the auxiliary qubit. So in this way, we can realize all the functions that are polynomials that have a definite parity. And the complexity that we need scales linearly with the degree of the polynomial that we have. Okay, how do we apply it to find a new version of HHL? So let's take a Hamiltonian that's, okay, the operator norm is less than 1, and let's say that the smallest eigenvalue in magnitude is 1 over kappa, so kappa is the condition number. Then we will, like if we want to obtain H minus 1 psi in this fashion with this eigenvalue transform, we will need a polynomial that approximates the inverse function, because of course 1 over x is not a polynomial. And actually we will need, like since all the eigenvalues of H in absolute value lie between 1 over kappa and 1, we will need an approximation 1 over x as a polynomial only in this range. So let P be an approximation of the inverse function in this range. And here you notice that we needed to normalize this function, because here in the hypothesis requires the polynomial to be less or equal than 1, while of course this this 1 over lambda will be larger than 1 because lambda is smaller than 1, and we normalize in this way to enforce this requirement. So we suppose we have a block encoding of H, and then we can build, as I showed you before, a block encoding U tilde of P of H. And this means that, let's say that we have this block encoding U tilde. If we apply this U tilde to a state of the form 0 tensor psi, so U tilde is a block encoding of P of H, and then we'll have this form. And 0 tensor psi can be seen as a vector like this that has psi in the upper component and 0 in the lower component. So this matrix applied to like what we get on the upper part P of H psi, that's what we wanted. And then in the lower part, we get some garbage. So we get 0 tensored with what we want, plus 1 tensored with some garbage. And this should remind you of what we had, like we had a similar situation also for HHL. And then we can measure the auxiliary qubit and condition on getting outcome 0. And then, of course, we get this state in the output, which is proportional, which is roughly equal to H minus 1 psi over kappa. And as before, the probability of post-selection is at least 1 over kappa square that can be increased to 1 over kappa by the trick of amplitude amplification that can be used also these times. Now, if you want to know what's the complexity of this, you need to know what degree do we need to approximate the inverse function as a polynomial. And then there is this result. So if we want to approximate the function 1 over k lambda for lambda in the range between 1 over kappa and 1 with precision epsilon over kappa, and we have the 1 over kappa here in the precision because we have divided by kappa the function, the inverse function. So this will correspond to approximate 1 over lambda with precision epsilon. So the required degree of the polynomial can be shown to be order kappa log kappa over epsilon. And then you see that we are having the exponential improvement in epsilon because 1 over epsilon appears inside the logarithm. So I told you that we have a success probability 1 over kappa, and then we have to repeat this algorithm kappa times before success. And then the overall complexity of this is order kappa square logarithm of kappa over epsilon, which is the number of calls to U which are required to run the algorithm. You will have noticed that there is no dependence on the size of the Hamiltonian H, but this cost is actually hidden in the cost of applying U once, because U is a block encoding of H, and of course the complexity of implementing U once will depend on what H is. So if you want to have an idea on how this polynomial approximation of the inverse function looks like, you can find it here. So this is a polynomial approximation of the inverse function in this range, with the constraint that the polynomial has to lie between -1 and 1 in the whole interval -1, 1, because this was the requirement for the singular value for the eigenvalue transfer to work. And I think the degree of this polynomial, it's roughly around 80, if I remember well. 80, like 80. And you see, you can get a quite good approximation in the required window. Okay, and then to conclude, of course, all the fundamental part of this singular value transformation is how to find an efficient block encoding of a Hamiltonian, of our Hamiltonian, but then there is this result that comes to our rescue that roughly tells us that sparse Hamiltonians can be efficiently block encoded. So let's A be our sparse matrix. Let's assume that's order 1 sparse, in the sense that each row and each column has only order 1 non-zero entries. And let us assume that all the non-zero entries have absolute value at most 1. Then there exists an approximate block encoding of this matrix A, such that applying once this block encoding requires a number of elementary gates that scales as number of qubits of the Hamiltonian. So this small n is number of qubits and is the logarithm of the dimension, plus logarithm of 1 over epsilon to the 2.5, where epsilon is the precision that we require for the approximation. Okay, and then we will need this number of gates and an order 1 uses of some oracles that we will need that can give access to the position of the non-zero entries of A and to the values of these non-zero entries. So if A is sparse, there are no issues in finding an efficient block encoding without significant overheads in the complexity, but of course the complexity of the block encoding will depend on the size of A, and the dependence is linear in the number of qubits as in the original HHL algorithm. Okay, that's all I wanted to tell you in this lecture. These are the 2 main references on the quantum eigenvalue transform and on the singular value transform. So the first is a tutorial, which is probably the easiest starting point if you want to start studying, know more about it. And the second reference is a more technical paper that contains all the technical details and the proofs of the theorems. That's all. Thanks for your attention.
Thank you, Giacomo.